So there's the rule, required strength in LRFT. This is what's in the spec. Less than or equal to a factor phi times R sub n. I'll explain all this stuff. Allowable stress design says required strength in allowable stress design is less than a quantity R sub n divided by the quantity omega. I don't know how that works in your head. It works a lot better for me if I reverse that. If I say, I'm usually calculating the resistance. So if I say the resistance has to be greater than or equal to the required strength, somehow that processes much more easily in my ears. It's just the first two lines reversed, and of course is the equivalent. But I see it better this way. Okay. The result then is I would say that the resistance, R sub n, knocked down by a certain value, because we don't know everything, has to be greater than what my analysis says I need, or equal. Well, the R sub n quantity, you notice, appears in both of those, each of those. And that's what we're dealing with. So regardless of which system you're working in, you're going to calculate, whether you know it or not, and now you do know it, you're going to calculate the resistance of a bolt in shear. And then you're going to use it in either allowable stress design or LRFT. So we are at this stage, you are at this stage in the United States, where the two systems do have a linkage, and it's a legitimate way of doing it. Going back to something that I introduced earlier, I said, recall, that the ASTM spec said here are our rules, but you must use them in accordance with another set of rules. Now we're at the AISC specification. It says here are our rules, the design rules, but you have to conform with what's in the Research Council and Structural Connection specification. So each of these outposts is pointing back to this common body of knowledge, and I'll show you where to pick that up, and suggest that you should be somewhat knowledgeable about that. It's a free download, it's easy reading, like that. We'll leave that aside now for a while. We've introduced the product, we've talked about the loading, we've talked about the forces and the systems in which we have to work. Let's get these installed at least a little bit. You'll notice throughout, and it's the same for any speaker, you've always got 3 or 4 balls in the air, and you hope by the end of the morning, or the afternoon in this case, that you've captured them all. Sure hope so. So there's what's happening. That person has a spud wrench in their hand. A spud wrench is an open socket hex type thing with a pointy end. The pointy end is useful for spearing your buddy's lunch or lining up holes. Useful tool in bringing things into installation condition. The possibilities for us that the bolts are snug tight only, I'll explain what I mean, or they're pre-tension, they're pre-tension, and we can pre-tension using a system called calibrated wrench, or by turn of nut, lots to come, or by other means. And these other means, while not as common, are in standard use, and they're valid. And we'll look at tension control bolts and the use of load indicating washers. So as a result of the installation, about which we'll have to discuss quite a bit, to state the obvious, the bolts are either pre-tensioned, meaning snug tight, or they're not pre-tensioned. They have a preload or they don't have a preload. What's the preload he keeps talking about? The preload is, there's the fastener, put it into the material I'm going to connect, and I turn the nut down. What happens? It comes up against the connected material, but I keep turning, and what happens is it elongates the bolt, doesn't it? And the bolt is saying, hold it, you're pulling on me, I'm going to resist that. That's the pretension. It's not more complicated than that. That's the pretension. So how do we get it? What level do we need? How do we inspect for it? That's all going to be revealed unto you. Now, if the bolts have a pretension, if I decided that we need that, we'll deal with that and the inspection issues that go along with it. Those are some generalities. They're important. Here's a real joint. This is the result of a real joint. Big joint. I think there are 28 bolts there. And the bolts here were preloaded, so we have tension in the bolts. So the parts are clamped together, and there's going to be frictional resistance. Let's see what happens. This is what I call the big picture. And in the initial region, from 0 to, I don't know, 180, it's fairly linear. Depends. A lot of these things depend on the proportions of, in this case, your plates. But at a certain level, the slip resistance will be overcome, and that's light. And the slip resistance is overcome, and it moves suddenly. It can move in a series of small slips, or it can move in one big slip or maybe two smaller slips. It doesn't matter. You get, as far as you're concerned, you get to the same point. In this case, this would be a deformation of, let's say, 3 millimeters. Okay? So there we are. It's slipped. Is this a limit of usefulness? Well, it sure is for bridge people. I mean, they have to be concerned about this. But has the structure fallen down? No, it hasn't fallen down. It's still there. It exists. It's got some slip in it. We'll talk more about whether that's something we can live with. But this goes on. And we've got a lot of life left. So we keep on with the loading, and the initial region is reasonably elastic here. But things start to yield, and it starts turning over, and then there's some strain hardening going on, and ultimately there's failure. What other information can we get out of this? What's failure? Oh, you know, fracture. Fracture, things have fallen apart, and we would all agree that we can't go past that point. It would represent a limit, however. But look at how much deformation there is in this big joint. But what do we got? About, I better look over here. About, well, almost 20 millimeters, maybe 18 millimeters. Can you work in millimeters? 12 millimeters is a half an inch. So give you an idea. 25 is an inch. So we're at about, I have to work backwards. We're at about 5/8, say, something like that. 3/4. That's a lot of deformation. Is that a good thing or a bad thing? Generally speaking, it's a good thing. We want ductility. We want warning of failure. We want to be able to allow for redistribution of loads in our system. These are all good things. So a lot of deformation is in principle a good thing. Okay, I think we've got the information that we need out of that. So the issues are the shear strength of the bolt. It can be in single shear or double shear. There can be threads in the shear plane or not in the shear plane. We have to discuss all this stuff. The bearing capacity of the bolt, I identified that early on, but then I kind of dropped it. The fact of the matter is, and what I'm telling you now, is that there's bearing in the bolt, and then there was bearing in the connective material. The bearing in the bolt is always, underline that, greater than in capacity than the bearing in the connective material. So we only check the connective material. So yes, there is bearing in the bolt, but it's never critical. Then there's the bearing capacity, what we call the bearing capacity of the plate. We tend to say the bearing capacity of the bolt. It's the bearing capacity of the plate, not the bolt, but we've gotten used to that. And then the member design, I'm showing it for tension, but if the member is a compression member, then everything, of course, reverses, and there's no difference as far as our bolts are concerned. Now, with the pre-tension bolts, they're in holes that, of course, are larger than the bolt diameter. You can't drill 1-inch holes to put in 1-inch diameter bolts, to state the obvious. So you make them 1/16 of an inch larger than the bolt diameter. We can also have oversized or slotted holes, but we'll discuss that later. Now, the amount of slip possible, if you sit down and figure that out, is 2 hole clearances. So 2 times the 16th, we're at an 1/8. So it could be 2 hole clearances of slip. Is that a bother for you? Is that a concern for you? I shouldn't say bother. Is that a concern for you in your structure? You may be able to answer, no, it's not, or yes, it is. I'll try to give you a little more background information. So we'll come back to that. Now, if slip is a problem in the sense of fatigue, and the parts are, by definition, if you allow the slip and it's fatigue loading, like a bridge, crane structure, the parts are slipping past one another. And that means that one surface is rubbing on the other. And that's not permissible, and I'll show you why. So slip and bolted joints, as I've said, can be as much as 2 hole clearances. In fact, when you put that joint together, some bolts end up in the middle of the 2 holes. Some are on the right-hand side, some are on the left-hand side. That's the way it happens. You never get 2 hole clearances of slip. Typically, based on measurements, both in the laboratory and more importantly in the field, it's about a half a hole clearance. So now we're down to, what was the hole clearance? An 1/8. Now we're down to a 1/16. Now you should ask the question, is that much slip going to affect my structure? Standard holes. What's the dimension now? It's about the thickness of a dime, just to give you some physical connection with this. My premise is that we should not be specifying slip critical connections unless we need to. You have to know when you need it, like fatigue. That's the most obvious example. I'll give you some more help as time goes on. But don't do it just because it's the more conservative of the 2 choices. I mean, we're competing with other people out there and other industries out there, and we don't want to make our steel structures more expensive than they need to be. So if you don't need slip critical connections, don't specify them. And for buildings, almost all buildings don't have to have slip critical connections. Now, bolts and shear type connections. It's common, we know that. Specifications distinguish between it's bearing only or you have to worry about slip. We'll discuss those in detail. Just a caution that if you are designing slip critical, it's your bridge. Yes, slip can happen in the bridge. I mean, we're always talking about what could happen. In the bridge, slip could happen. But that's not the end of the structure. So that structure still has to be checked for, quote, shear and bearing. Whether you're using LRFD or allowable stress design, and we are in the slip critical category, that's the one I'm illustrating with. Yes, you have to check for slip, but you also have to check, after you've done that, for shear and bearing at a different load level. So let's deal with the bearing type connection. The issues will be the bolt shear strength, the bearing capacity to connect the material, and the member strength if we want to do that. Now, this next statement is the first thing I've said to you that's not intuitive. All the rest, you're able to sit back there and say, I knew all that. Well, I hope you did. This one is not intuitive, and if you knew it, that's great. But I'm going to have to work on the basis that you didn't know it. And that is that the shear strength of the bolts, about which I have to talk quite a bit yet, it's not dependent on whether I pre-tensioned the bolts or didn't pre-tension the bolts. So this group over here, they pre-tensioned their bolts. That group over there did not pre-tension the bolts. The majority in the middle didn't know what to do. They're going to await the outcome. And the answer is, I'll have to show you why, it doesn't matter whether this group pre-tensioned and that group didn't pre-tension. The shear strength of the bolt is going to be the same. Okay? So that big picture thing, I'm talking about, I'm going to expand on this region after slip. Why do I do this one first? I have to pick one. That's all. It kind of reinforces, however, the fact that I think most of our design should be in this region. And then we'll do the other region afterwards. Okay, bolt shear strength. We're going to do the tension test. We have to know what the relationship is. Our product is in shear. What's the relationship between our acceptance test, which was in tension, and what I'm dealing with? And now you go again back to second year and you say, oh, what's the relationship between shear and tension on a fundamentals basis? Well, it's second year. It couldn't be that bad. So you think and you think and you think, and you think, von Mises. I remember that guy, von Mises. There's a theory of failure. There are a bunch of theories of failure. His theory of failure works particularly well for this case, and it says that those guys that do the shear test, and then those people that, those people who do the tension test, and those people who have to use the product in shear, they need to have to get together and sort that out. And the get together is that the bolt ultimate shear strength is about 62% of the bolt tension strength. The von Mises yield criteria says that relationship should be, and now you do remember, 1 over the square root of 3. Oh, yeah, 0.577, 0.58. Well, theory and practice never fit quite together. That's pretty close, and we accept that. I'll show you the type of test that's used to obtain the bolt ultimate shear strength. Now, your design rule says, okay, the 62% will go along with that. The bolt is an A325. Ultimate tensile strength is 120. Take 62% of that, and you've got the bolt shear strength, right? Right. Your specification immediately says, discount that by 20%. I'm going to have to explain that to you. It asks whether you have threads in the shear plane or not. Obviously, if I have threads in the shear plane, I don't have as much area as otherwise. And also, if I have a long joint, meaning long, 3 or 4 feet, then I have to have another discount. So all of these things have to be dealt with. There's the test. If you look at the inset, the test says set up a little jig like that. Pretty simple test. Load it and see what happens. And the result is the load. These are, I've got them in stress versus deformation. Could be load versus deformation, or stress versus deformation. The A325 bolt like that, and the A490 bolt like that. And first question I ask you is, do you see a shear yield point? These are real curves. Do you see a shear yield strength level? No, there isn't one. You know, I realize I'm blaming you for the sins of your fathers. You know how that goes? Wasn't really a bad sin. But don't base a rule on shear yield, because there isn't a shear yield. It just doesn't happen that way. What else can we get from this piece of information? Well, the 325 bolt has an ultimate deformation on back to inches of about 0.2, more or less. That's good, eh? A lot of shear deformation. The A490 bolt clearly is stronger material. Not quite as ductile, still got lots of deformation. So we get a lot of shear, whether I'm dealing with bolts or something else. Shear is it's very forgiving. It's got a lot of ductility in it, just inherently in how it's happening. So that's the information. That's good information, good basis upon which to write a rule. There's physically what's happening. These are, just to give you the scale, these are 1-inch thick plates. 4 of them, push down on the middle 2, react on the 2 outer ones. The test was taken to a certain point and then stopped. Then there was a saw cut made, so you see the threads of the bolt, you see the washer, you see the rest of the stuff. I'm trying to get information to you, and I'm not going to just give it to you. So let me ask it as a question. Do you see the bearing stresses? I mean, this is just a manifestation of the free body diagrams that I was using earlier. So there are 2 questions. Do you see the bearing stresses? Question 1. Question 2, do you see the shear stresses? Any time that I ask a question and leave kind of a time gap there, it's a signal to you that it's not the obvious thing. You can't see stresses. You can't see any kind of stresses. You can't see shear stresses. You can't see any kind of stresses. But we do see things. What do we see? We see deformations. And our thinking should be about deformations first and the consequence, stresses, afterwards. If I ask the question this way, do you see bearing stresses? Do you see shearing stresses? Then it's much easier. What did I say? I said stresses. Do you see bearing deformations? Do you see shear deformations? That's easy. You do see those. And then you figure out the stresses accordingly. So there are the shear stresses. Do you see the shear stress now? That's a lot of shear stress. A lot of shear deformation. I'm caught in the loop here. You see a lot of bearing deformation. You see it. You see it here. You see it here. You see it here. It's easy to see the bearing deformations. It's easy to see the shear deformations. And from those, we will get the stresses. Okay, good information. This is the, these are the last 4 bolts in a line of, gee, I think it was 13, and 8 inches of grip now. And I've just, you know, I'm not going to show you the whole picture because they didn't saw the whole joint. So we got the 4 inner plates going to the right and the 2 outer plates, top and bottom, going to the left. And what do we get out of this? Well, quite a lot of bolt bending. That's illustrative. We see that one fastener has failed. There's one shear plane failed here, and then the test was stopped. With this number of bolts, you can stop the test when one has failed if you're very, very careful about it. Okay? I'm going to look at another illustration before I explain the features that I want. It's the same thing, but with a much smaller joint. This is the one that's 13. The previous one was 25. It's coming back to me now. So this was 13 bolts in line, and the proportions were different. You have to keep in mind that what we see is a reflection of the proportion of the bolts as reflected in the shear capacity and the plates. All right, 1-inch plates again. For a big prize, what can you tell me about this? I'm trying to get you to think, and it would be nice if you could do the answering right now, but I realize that we're not in that position. But what is there about these 4 bolts at the end which are part of 13? Well, I've tried to encourage you in the last few minutes to think about deformations. Look at that top bolt. Look at the deformation. Look at, let's go 4 bolts down. Look at the 4th bolt down. Look at the shear deformation. They're very different, aren't they? What does that mean for us? It means that the shear load carried by the top bolt is a heck of a lot more in this illustration than is carried by the 4th bolt down. We cannot take the total load and divide by 13 to get it. We can get an average, but it won't be valid. It's just too far out. Now this has been set up so that the imbalance or the deviation from average is pretty high. But nevertheless, it's true, and the specification has to take that into account. If you have 1 bolt in a joint, it carries all of the load, shear. If you have 2 bolts in a joint, they each carry 50%. If you have 3 bolts or more, they don't carry 1/3 or more. So we have to deal with that. Here's what's happening in a fast and dirty way. Let's go from left to right, as we usually do, and say, well, as I go past that first bolt, it takes out some load, but the stress in the lap plates will be very high because I've only taken out a little bit of load. I don't know how much it is, but I got a lot of bolts to go, so there'll be a high strain in there. By the same argument, coming in the other direction, there'll be a low strain in that region in the main plates because most of the load has been taken out as I go from the right-hand side inward. There's a high differential strain. If I head for the middle, somewhere it's 50-50. Don't know where that is, but well, somewhere it's 50-50. So it's a high strain at the end. It's a lower strain as we go towards the middle, and that's what you saw in the previous illustration, where the shear deformations clearly varied from the end as we went down towards the middle of the joint, and we have to take that into account. Just before I leave that illustration, or I have left it, but I want to say before I leave that part of the topic, we're talking about tension or compression splices, meaning actually loaded members. This case where you're transferring load out of the web of a beam into a column flange, it doesn't have that redistribution of forces that I've just been showing. These can very safely be assumed to be equally loaded. And I think the specification says that. Okay. All right, we've got a bunch more information. And again, something new, but reverts back or relates back to what I said earlier. I said it didn't matter whether the bolts were pretension or not pretension. They had the same ultimate shear strength. So I have to justify that. So you see the little test going on here, and there's some information. And up above is the characteristic of the bolts that are being used. Let's deal with the top part first. So you put the nut on, you turn the nut, that's called torquing or applying the torsion. The bolt elongates, it develops a resistance. At some point that curve turns over like that. Okay, that's just almost common engineering sense. So we do those little tests, shear type tests, down in the lower insert. And let's suppose, for sake of argument, that we put on a half turn of nut. That's going to be one of our standard installation procedures. So let's fly a line in to the half turn. And the test results are down here, and it shows that in ultimate shear stress terms, forget about the units, it's about 107 whatevers. Okay? There are 3 tests, and they're clustered like that. What's the pretension in that bolt? Well, look up here, and it's about 60 units. Kips, you know what kips are. Okay? Just file that information away. But somebody puts his bolts into 1.5 turns, which is not a permissible value, by the way, but he did. He's felt energetic that day, and he put on 1.5 turns. And you say, wow, he's destroyed everything. Well, as it happens, there's still a very high pretension force in there. It's about, I don't know, 59, 58 or something like that. Let's look at the test results that were done with bolts that were installed to 1.5 turns in the shear test. And they're here, you see them, and the line is there already. And the pretension, I just said, is 58. What's the shear strength? Well, admittedly, it's a little less than the previous tests, but not significantly, 105 or something. If you do enough tests, these are the same, trust me. Meanwhile, somebody said, I don't need to turn the nut on at all. I'll just do snug tight. And the pretension in this case is sitting in there, and it happens to be 8. I know what it is because it was set to that value. And the pretension now, the line is there, is 8. And the test results are, I don't know, 103, 104, something like that. There's just, statistically, once you've done more tests than 3, there's no difference in the ultimate shear strength among, in my illustration, 3 cases being snug, half turn, or 1.5 turns. Okay, that's proof, but I'm going to go a little further with it because I think it's not necessarily mentally easy to grasp.